Hey everyone, what's up? Today I want to say a couple of things about one of my favorite topics, in physics, which is circular motion. So you can treat circular motion from a scalar perspective, or you can use a lot of vectors and stuff in it. Today I want to show you that this equation is true using the definition of acceleration in polar coordinates, or at least a part of it. So basically, you've probably seen this before. Maybe you've only seen the scalar form, which is that AC is equal to v squared over r. This is just the vector form. The centripetal acceleration vector, and I should probably do a diagram of what type of setup I'm referring to here. Let's say we have something like, you have a circle. Let's imagine this is a circle. You have a center, and you're going to have this. Now, this will be a vector, let's say r. And because this is a circle, there's a very useful property, which is that I'm going to use this notation r, which will represent the magnitude of the position vector, is equal to big R. Big R is simply, it really would be the radius of the osculating circle along any given curve. That is really the formal definition of big R. But in this case, R will just represent the constant. Remember, it's a constant radius of the circle, okay? It's a circle that is not shrinking, or growing. So this R and this big R are constant, okay? And that will be important, and you'll see why in a moment. So this is the setup that we have. You may have some sort of mass or something, and you may have another smaller body orbiting that mass or whatever. This is basically a setup that we have. You have one thing going around another, and your origin is the thing at the center. So basically, I want to show you that v squared over r is indeed equal to centripetal acceleration, okay? So it turns out that the total acceleration vector in physics, or in math really, the second derivative of the position vector is going to be this. So we have this in polar coordinates, or really in r hat and theta hat components. When I say theta hat, imagine that we have, let's say, you maybe have an angle here, and one way you can describe how this angle is changing, you can just simply put a unit vector here and call it theta hat. And theta hat will always be, first of all, it will be tangent to this circle, and it will also be perpendicular to r, okay? So that is what I mean by theta hat. So basically, the acceleration vector, a, or r double dot, whatever notation you want to use, is going to be this. So you're going to have, I believe it is r double dot minus r theta dot squared times r hat. This is the magnitude of the acceleration vector along the r hat direction. R hat is the unit vector for this r that you see here. And then we have plus 2r theta dot plus r double dot, I believe. I should check this. Yeah, this is right. So I had to check because it is very important we get this right, okay? And honestly, this is not really something you should know off the top of your head. You should know how to derive it, but really if you don't memorize it, you can always look it up, as long as you understand what it's saying. Basically, the acceleration vector, is just gonna be the second derivative of the position vector, and you can split this vector into two components. A component that is along the r hat direction, which is very convenient because we're saying that this r is changing over time, which means that this r hat is now going to be constant, and you can express that magnitude with this scalar, and you can also express how fast, or you could say what is the acceleration along the direction of this circle using this scalar here, okay? Now I hope you're comfortable with dot notation. If you see a dot, that is the first time derivative, meaning ddt. If you see two dots, that's just the second time derivative. So ddt of ddt, basically. Now, today we are concerned with this term here. Centripetal acceleration is really the vectors defined like this. It's just going to be the acceleration, the component of the total acceleration vector along the r hat direction. And what I want to show you is that this is equal to this, okay? So really our goal today is just going to be showing that minus v squared over r, big R, is going to be equal to, we want to see if this is true, should be equal to r double dot minus r theta, r theta dot squared, okay? So I want to show you that this is true, and it is very simple. It is extremely easy to show that, okay? So basically, we're going to do the following. This is just going to be a direct proof. I will rewrite this into this. So first of all, what is r double dot? Well, we know r is just going to be the magnitude of the position vector. And we know that magnitude is equal to r, big R, the radius of the circle. Now, r dot should be 0 because big R is constant, meaning the magnitude of the position vector is constant. And if r dot is 0, r double dot should also be 0. So then we can cross this term out and say that this is 0, okay? Based on the argument I just gave you. So then this is nice. Yeah, I'm gonna continue over here. Now we have minus v squared over r is equal to big R is equal to, I'm gonna drop the minus, same thing. V squared over r is gonna be equal to r theta dot squared. Nice. And we can continue rewriting this like this. So r theta dot squared, okay? Because little r and big R, same thing, okay? We are in a circle, and for this specific scenario, we're in a circle. And now, what about this theta dot? Well, maybe if I do this, you'll know what to do. Remember, theta dot is really just saying d theta dt squared, okay? And hopefully, maybe you've seen in your physics class that this is what we call omega, okay? So omega is just going to be how fast this angle is changing. And now we would like to rewrite omega in terms of v, because that is what we're trying to show that it's equal to, okay, that these two things are equal to. Now we know that, I'm going to start from the basics. Maybe you know that let's say this is the length of an arc, is going to be equal to r times theta. This is just a math equation, something you learn in math class, which in our case will be equal to r theta. These two, again, these are just the radius of a circle, or equivalently the magnitude of the position vector. Now, if you differentiate this with respect to time, what you're finding is what is the rate of change of the length of an arc, which is just really angular velocity. That will be proportional to how the angle changes, okay? So then you have that v, let's say, this is really a linear distance. That is also something you should keep in mind. Although it's like curved, it's really a linear distance. V is equal to big R times d dt. So really, I think I should do this. I don't know how familiar you are with this, but I don't want to have anyone in the comments saying that I didn't prove something. So let's do this. Let's say that dl, that's an L, looks kind of bad, but that's an L. dl dt is going to be equal to r. R is constant, so we don't differentiate it. D theta dt, and this is what we're going to call v, linear velocity, linear speed, not velocity, linear speed. And this will be equal to r omega, okay? And that's amazing, because then we can see that omega is going to be v divided by big R. And then we can just throw it in there, and I think you can see that everything follows pretty simply. We just have v squared divided by r. That's the left-hand side. It's going to be r times d theta dt, which is going to be v over r squared. And then, you know, I probably should stop writing now, because you know how it goes. You get this, you get this, and from this, well, perfect, okay? You know, the 2 r's cancel, well, 2 r's go away, and then you get that this is true, which is nice. I should probably do this. No, nice. That's it. This is a proof. I don't know if I would call this a proof, but I think if you're taking physics and you know a couple things about vectors, it may be pretty useful to see this and to see how this is true from a more fundamental equation or something more general. This is a more general case than this. This is a specific case in which you don't have theta hat component of acceleration. If you're accelerating along your trajectory, along the direction of your motion, meaning along the direction of your velocity vector, then this would be a non-zero term, and this simply doesn't work. No, well, would it work? No, it would actually work, yeah, because we're saying that this is just centripetal acceleration, okay? But this is just focusing on one term of the entire acceleration vector, okay? So if you have a more complicated scenario, you're gonna have a theta hat component, and then you can't say that f equals ma sub c. You have to say that f equals ma this, okay? So I don't know. Hopefully you found some of this useful. I just like talking about this. I think if you're taking physics and you didn't know a couple of these things, then well, now you know at least why this is true and how it comes from. This is just a theorem, you could say. This is just a mathematical truth, and this is maybe a bit of a derivation, okay? So hopefully you enjoyed this. Hopefully you learned something, and see you in the following video. Bye.